Okay. Hello everyone and welcome to today's Tea Times. I'm Annie Gao, the Outreach Chair of SWIP and the host of this event. First, let me introduce today's speaker, Professor Decker French from Astronomy Department. Professor French received her bachelor degree from MIT in 2011 and got her PhD degree in 2017 from the University of Arizona. She was a postdoctoral fellow at Carnegie Observatories before she joined UIUC in 2020. Now let's invite Professor French to talk about herself and her journey in physics.
Okay, thank you. Let me share my screen. Oh, I think you need to enable participant sharing, sorry.
Yeah, let me do that. Okay, yes, I think now we can.
Okay, perfect. All right, can you see my screen?
Yes, yeah.
Okay, perfect. All right, so yeah, thanks for having me. So my name is Professor French, and I just started in the astronomy department here at Illinois. So I figured I would tell you a little bit about my career and how I got here, and then talk about some of the research that I'm involved with at Illinois. So a little bit about me. So I grew up actually in Illinois, in Arlington Heights, around the suburbs of Chicago. And I went to MIT for my undergrad degree. I majored in physics. I knew I wanted to do physics when I was applying to school, but I wound up also double majoring in planetary science when I got there. That was mostly just related to, I knew I wanted to do astronomy, and between my astronomy minor and taking a bunch of courses in weather and meteorology, I actually wound up with being like one class away from the double major. So I went forward and double majored. So when I was kind of in late undergrad, I decided I wanted to go to grad school, but I didn't really know in what. So I actually wound up applying pretty broadly to schools in both astronomy and physics. And in the course of applying and talking to more faculty and visiting schools, I decided to do more of an astronomy track. So I wound up at University of Arizona in 2011 in their astronomy program. And so there I worked on a few projects in astronomy. I worked for the same advisor the whole time, but I wound up switching topics between a few different areas of astronomy while I was there. So when I started off, I was doing more of a theoretical project on cosmology and gravitational lensing. But then I switched into some galaxy evolution work that I'll talk about later. And that led us in some interesting directions that led me to kind of add on a second topic of expertise for my thesis that I'll talk about as well. So while I was at Arizona, I also knew I wanted to teach, and I wanted to try to get good at that. Sorry, my dog is barking in the background. I knew I wanted to get good at that. And so I taught at Pima Community College in Tucson. You can generally teach at a community college once you have your master's. And so for me, that was a great opportunity to get some experience teaching and see if that's really what I wanted to do. All right, so after I graduated in 2017, I was a Hubble postdoctoral fellow at the Carnegie Observatories. So those are in Pasadena. For historical reasons, the actual observatories used to be up on Mount Wilson above Pasadena, outside of LA. But as you can imagine, the light pollution in Los Angeles is pretty bad for an observatory these days. So the actual telescopes that we use now are down in Chile. So for me, that was a great opportunity to do a lot of observational work using the telescopes down in Chile, flying back and forth way too much before COVID, and getting a lot of experience. So I just started a few months ago then here at Illinois as an assistant professor. So let me tell you a little bit about some of the work that I've been doing and some of the stuff that I will work on here at Illinois. All right. So, well, yeah, and even though this is a recorded talk, if you have questions, definitely feel free to send me an email. it maybe will be posted along with the chat. Otherwise, find me on the Illinois Astronomy page, and feel free to ask any questions later on. All right, so one of the things that I've been working on lately is our tidal disruption events. So these are what we see when a star comes too close to a supermassive black hole, such that those tidal forces from the extreme gravity are stronger than the self-gravity of the star, and it can tear the star apart. And there's a little movie with this, which might work. Hopefully you can see that. Yeah, the little artist's conception of what that looks like. So as long as this disruption happens outside the event horizon of the black hole, we'll see a bright flare as all that material is accreted onto the black hole. So these events were predicted by theorists in pretty great detail as early as the late 80s, but they've only really begun to be discovered in significant number, in part because now we have a lot of surveys that are scanning the sky on a nightly or every several night cadence looking for supernovae. And these tidal disruption events are about as bright, if not a little bit brighter than a supernova, just more rare. So surveys that are looking for transients that are now finding thousands of them are finding a few tidal disruption events every year. So these are the artist conceptions of what that looks like. But let me show you what it looks like in our actual data. It is considerably less exciting, considerably less pretty, but I think still pretty exciting. So here's what that looks like. You can see my pointer. These surveys, you have a reference image of a patch of the sky. So here is a galaxy that we have a pretty coarse image of here as a reference. And so this is from a survey called Assassin, the all-sky automated survey for supernovae. And what they're doing is they're looking at this patch of sky every few nights and looking for changes. So if you have this big reference image, you can subtract off the nightly image and look for kind of a dark spot that would tell you that there's extra light in the new image. So you can see this timeline. So this starts in June of 2014. And you can see that there's nothing in this image, right? Just kind of noise, 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 noise. And then there's maybe a little bit of something, and then a significant detection, where you can see in November of 2014, there was a bright flare of light in this galaxy. All right, so this is how we find these events in finding these flares of light. But you might wonder, how do you know that this particular flare was a tidal disruption event and not something else, a supernova, or even something more mundane, like maybe there was an asteroid that just went right past that galaxy and we got unlucky? Well, the way to do it is to get a spectrum of the events. This light is what we call like a broadband image, where you're getting light across a pretty wide swath of the electromagnetic spectrum and the optical. But what you do then is train your spectrograph on that very center and do something like this. So here's a plot of the flux versus wavelength and the optical. The rest were optical for this case. It wasn't that high for each of the thing, and what that looked like. So this black spectrum is a spectrum of the galaxy from 2007. So when this was taken, we had no idea that there would be a transient in this galaxy, but it was part of the Sloan Digital Sky Survey that got spectra of a really large number of galaxies. In red is what was seen in late 2014 when this event was discovered. So you can see that it looks very different. And it has, in particular, this broad hydrogen alpha line that's indicative of this being a tidal disruption event instead of something like a supernova. And so people have been finding more and more of these events in the past decade or so, and they have these characteristic broad lines. So here's another example of a really broad event that was discovered in 2010 by Zari et al. So here's a plot of how bright it was, the magnitude versus the time since it was disrupted. And you can kind of see that in all these different colored bands, or the near ultraviolet, and then in the optical bands, kind of rises and falls over a few months. And a spectrum of this event that was taken, I think right around the peak, yeah, data -22, right around here, shows that it has a lot of blue light, and it has kind of these broad lines that tell us something about what this really is, and it can let us kind of diagnose this as a tidal disruption event.
Actually, Professor, I have a question.
Yeah.
What's the observatory look like? Is that you use like the physical telescope that we use on our campus, or it's like a rocket that you put it on the in the universe, like around some like anywhere to observe this events?
Yeah, great question. So the data that discovered this, this is from a network of really small telescopes that are operated by Assassin. By small, I mean like just really a few inches. These are small telescopes, but they're in really dark sites. So having one at Illinois would be hard just because of all the light pollution from living in a relatively dense area. But the Assassin telescopes are in dark sites well away from people, and they're all robotic. That way, no one has to go and observe them every night. They can kind of schedule it in advance, and with a lot of hard work and getting it set up to run smoothly without human operation, it can just kind of run. And so there's a lot of these networks of smaller telescopes that have been put online as robotic telescopes get more and more reliable. And this is really exciting because you can see how quickly this object evolves. This is you can see like there's like 3 nights between some of these. And you can imagine if you had a week of bad weather, you would lose that information about this light curve. Having telescopes in multiple dark sites lets you kind of overcome weather challenges. Because let's say if you have a telescope in Chile and it's cloudy there, well, maybe your telescope in Hawaii can pick up the slack and give you still a good kind of evenly sampled light curve. So to get just the light to detect these and look at the light curves, fairly small telescopes were used. Anywhere from really just a few inches up to a meter or so are commonly used. And those are all ground-based facilities.
Okay.
And then for the spectrum, getting this information, typically you need a bigger telescope because you're spreading the light out more. So you need more light to still have good signal to noise. And these are bigger telescopes, 2 meters all the way up to 8-meter telescopes are typically used for these in the optical. So again, dark sites. So Chile, Hawaii, Texas, all over. And so what I'm showing you here is really just the optical picture. But of course, that's just a small part of the electromagnetic spectrum. And these objects are also bright in the radio and the X-ray and the ultraviolet. And so for those, a ton of different telescopes are used. These objects are often bright in the X-ray and gamma ray. And so for those space-based satellites are used. Just because we're not getting that light on the Earth. Fortunately for us, right? The atmosphere filters all that out. And then in the radio, these are commonly observed with like the VLA using the big interferometer, which is useful because you can get a really accurate localization, right, of where the event is within the galaxy. This picture is a little bit, you can see it's like really low resolution. That's by design. They get better sensitivity by having the low resolution. But you can see trying to figure out where exactly this event is compared to the reference image. Even if you had a slightly better optical picture, would be tricky. And the radio being that much more precise can really help with that. Yeah, so yeah, great question.
Yeah, okay, thank you.
So the thing that I've been working on at these events is now that we have more and more well-characterized events. So the few I'm showing you are from 2010, 2014. We started to find something like 2 events every year. In the last year, that's kind of grown to more like 10 events every year, which is really exciting. So we can study the events as like a population. We're not doing the stamp collecting, right, that you might have heard business joke about. We can really study these as a statistical sample and look at them as a whole population. So what I've been looking at is the kinds of galaxies that these events happen in. So we know that the supermassive black holes are tightly correlated with the galaxies that they live in, because the same processes that can drive the black holes to grow also grow the galaxies to form stars. And so I've been looking at the kinds of galaxies that host these events to try to look for connections. And so when I say what kinds of galaxies host the events, what I really mean is what kinds of stars are in the galaxies hosting these events. So you might have seen a diagram like this before showing what the spectra look like of different kinds of stars. So when we look at stars, we see that there's different absorption lines, these dark patches in their spectra that look different depending on the different color of the star. So up here, these are O and B type stars. They're very massive and they're very blue. They don't live for very long. Versus down here, you have K and N type stars. They're less massive, but they live for a long time. They're very red, and you can see they have these big complexes of metal lines in their spectra. And then in the middle, you have kind of intermediate lived stars, and especially these A-type stars, you see that they have these really deep bottom absorption lines that you can use to kind of age date, right? You can use to tell the age of the stars. Basically, galaxies that have these super short-lived stars have to be constantly making new stars because they're so short-lived. They would only be there if they're constantly being replenished in the galaxy. Versus every galaxy will have these long-lived red stars just because once they've made them, they'll be there for 10 billion, if not more, years. So if we look at the amount of light in a galaxy that's coming from these different kinds of stars, we can get a picture of the history of how that galaxy has made stars over time. So a different way to kind of picture this is if you have a young star-forming galaxy, so this is kind of like our Milky Way, where it's still making more stars. A lot of its light will be blue from still having all these young, short-lived stars. Versus a galaxy like this, an elliptical, we call these red and dead galaxies because they don't have any young stars left. They did in the past, and they made these older-lived red stars, but all of the younger blue stars have long since died off, and they haven't been replenished. And so when you look at the spectra of these galaxies, you see these different kind of amounts of the different populations of stars. You can kind of think about this as like the eigenvectors of what goes into making the light from a galaxy. That doesn't work out with math because they're not like orthogonal, right? But I think you get what I mean. And so what I've been looking at are these features of the intermediate age stars. So if the O and B stars are only lasting for maybe 5 million years or less, and the M stars are lasting for 20 billion years, these stars last about 1 billion years. So these features tell something about the intermediate history of galaxies. So sometimes we see galaxies that look like this, where they have some of this intermediate galaxy light, but not the youngest light. I think these are kind of in the middle, galaxies that are evolving from blue and star forming to red and dead and done with star formation, have to go through some in-between phase. And we do see galaxies that look like this, that look like they're really kind of in between. And they have these big populations of what we call A stars that have those deep lines. So when we look at the kinds of galaxies that then host those tidal disruption events, which are going to happen just at really very nucleus of the galaxy, at the very center, much smaller than I could show, with pointing my mouse on even the high resolution pixels on this image. We see, let's skip ahead. We see, okay. I thought I put another slide in here, sorry. So picturing that in a different way, we can look at the blue light kind of from the current star formation in the spectra versus that intermediate light. So reframing these into axes on a plot, making measurements, you can say, okay, these galaxies are forming stars, these galaxies are red and dead, and we can find the intermediate galaxies here, right? They have like a mismatch on this plot, whereas these are kind of correlated, right? things that are forming stars now were also forming stars in the past billion years. Things that are dead now were also dead a billion years ago. Galaxies over here look like they have these big intermediate stellar populations, but they're not forming stars now. So they're in the middle of going from here, taking a jaunt over here, and going to these red-ended galaxies. When you look at where the tidal disruption events are, we find that a ton of them are in these transitioning galaxies that are on their way to ending their star formation. So this is the picture as of early last year, where you can see that we have a few events, but really enough to kind of make a picture where the events, the galaxies that are hosting these tidal disruption events are really different than the rest of the galaxies that are on this plot that haven't had an event. Such that basically half of these tidal disruption events are in weird galaxies. So I've been trying to work on why this is, and also use this as a tool, because you can see we have like 24 really well characterized events now, in late 2020, but that's going to get a lot better really soon, because we're entering this really amazing phase of transient observations. So until 2019, we were finding 2 TDEs per year, which is really exciting, new events, it's great. But starting last year, a few new facilities came online that are finding something like 20 events every year. And this is ramping up. 2019 had like 10 good events, and we should be ramping up as we go. But starting in 2023, or maybe later, because everything is kind of watched this year, but 2024, the Vera Rubin Observatory is going to come online. So this is a facility down in Chile that is going to scan the entire night sky down to depths of way fainter than any of these other telescopes every 4 nights. So whereas we're finding a few supernovae every night with these events, Rubin Observatory is going to find millions of transient events every night. If you've heard talks from people who work at NCSA and some of these groups using different techniques to work with big data, LSST in the Rubin Observatory is like this classic big data problem. There's so much data coming out of this, and finding these interesting events is like the proverbial needle in the haystack, where it's hard to pick them out. But if we can find them, there should be thousands of TDEs every year hidden within that amazing alert stream in the Rubin Observatory. So one of the ways that we can suss out these events is by using the fact that they have these weird host galaxies. So I've been working on ways to kind of pre-identify where we think the events might turn up, so we can better find them in the deluge of data that's going to come from Rubin Observatory. Right.
Actually, Professor, I have another question here. So when the stars are captured by the black holes, are they still able to like eclipse after that, like to run away? Because I see from the first slide, it seems that the star moved away, but I was thinking maybe the tidal effect will make the black hole to attract it and collapse and to disrupt it.
Yeah, so it depends a lot on the geometry of the event, of kind of how it comes in and how close to the tidal radius it is. If it's like just a glancing blow, or if it really just goes right in there. So for a typical event, about half of the star will get accreted onto the black hole and fall in, and about half of it will be flung out, and probably will not come back ever. That exact amount will depend, so it won't always be half and half.
Okay. So both circumstances exist.
Yeah.
Okay.
Thank you. Yeah, and sometimes depending on the structure of the star, just a small amount of mass could be kind of pulled off the star and accreted, and the rest of the star might survive intact, either to escape or maybe be disrupted again down the line. So yeah, lots of possibilities.
Okay, yeah, thank you.
Professor, I think so I just joined. So I have also a question here. So I think we didn't talk about like, is there any like angular momentum transfer between the like black hole and the star? For example, you just mentioned about like there's some star like scattering through the black holes, but there might be like some interaction, maybe like angular momentum transfer like between different stars and black holes. Is there kind of like a simulation or some observational data to show that?
Yeah, so people are working on trying to figure out what kind of how the history of a black hole affects what its angular momentum is. So one of the key questions is how fast are the black holes spinning? Because the picture where you have you only see the event if it happens outside the event horizon depends on there being an event horizon, right? But if all black holes are spun up, let's say if all the stars and all the gas that's accreted onto black holes come in the same sense, that will spin up and spin up and spin up and spin up the black hole over billions of years. And if they're all spun up, you should see these events around more and more massive black holes. Basically, it'll be harder and harder to have an event outside or inside of the event horizon if they're spinning, just with a different metric. And so one of the key ways to test this is to try to find these events around really massive black holes. So there's been one event that was found around a black hole that we really should have only seen the event if it was spinning at 99% plus. Maybe that's been revised, but I think it was close to that, of its angular momentum, max angular momentum. But that event didn't really look like the rest of the tidal disruption events that we've seen. Its spectra looked different. Its light curve, instead of having a smooth rise and fall, it rose and fell and then got brighter and then fell. And so we don't know if that's really a tidal disruption event or if it was some kind of weird supernova. I think it's a tidal disruption event, but there's some division in the literature. So really the key is to get more events.
Okay, great. That means so we somehow still have like a blank space between that because it's kind of we're lacking like in between there.
Yeah, it's definitely a space where more data is needed to fill in the space.
Okay, great. Thank you.
Yeah, and so this is one of the things that in the next 10 years we'll be able to really answer or find more questions, I'm sure, with the Rubin Observatory. Oops, I lost my focus on here. Somehow I lost the control, but let me just try again.
Yeah.
There we go. Right. Yeah. So one of the other keys to addressing the question you raised and others is it's helpful, like if you want to know, say, what was the black hole mass, right? Like, would you have expected to see a TDE outside the event horizon for this? It's really helpful to observe these events as early as you can, basically to discover them and know what they are as soon as possible. Because if you wait and say, look at the data years down the line, you won't have all the information you need. And so figuring out how to best identify these really early, something I'm working on in advance of Rubin Observatory, as well as other people in astronomy. All right. So I also want to talk a little bit about some of the work that I've been doing on how galaxies evolve. So this is where I mentioned that I kind of did a career shift mid-grad school. I had been working on how galaxies evolve over time, right, with this picture of looking at the transitional galaxies, and that's really how I got into this the space of tidal disruption events. But I started working on this question of how do galaxies evolve from forming stars, being these blue gas-rich galaxies, to the red and dead galaxies that have stopped forming stars and don't seem to have much gas left. This is one of the key questions that's been driving astronomers who study galaxies for basically 100 years now. Ever since we could look out at these different galaxies and know what they are, people have seen, well, the blue ones, they look disky, they have spiral arms. Sometimes you see them edge on, they look flat, versus the red ones, they're bigger, You never see them edge on. They're kind of round, and you don't see these spiral arms. So this dichotomy where there's really two different types of galaxies has inspired a lot of work trying to understand why. And as the physics of how we understand stars has come along, we have understood that the fact that the spirals are blue mean that they're continuously forming new stars, which is why we see all that blue light. But as far as how galaxies would go from the one on the left to the one on the right is still a subject of ongoing research. So the way that I've been looking at this is to look at the fuel for star formation. So we know that stars form out of dense gas and dusty clouds in galaxies. And so by looking at the fuel for star formation, basically asking the question, if galaxies stop forming stars, what happened to that fuel? We can start to address these questions. So to kind of illustrate what I mean by gas and galaxies, I like to use the example of Orion, which you can see in the sky brightly at night, especially here, especially this time of year. You can find Orion's belt. You can find the Orion Nebula below it. So here's an example of what it looks like if you can find kind of the three stars in a line in Orion's belt. It doesn't look like much with your eye necessarily, but if you look at it in the infrared, so here's an example of what that nebula looks like with the Spitzer Space Telescope. It looks like this. So you see these big plumes of gas and dust lit up. These are hiding young star-forming regions. So the Orion Nebula is one of the few places in our galaxy that's actively forming new stars as we speak. And so people study this as an example of a really detailed case study of how new stars are formed. But we can also look at this in other galaxies. Don't know why. Oh, I think that's supposed to be a. Don't know why there's. Sorry. Oh, there it is. It's a video, but it's not working. There it is. Yeah. So here's kind of an overlay of what you see at night with your eye, just in invisible light, and then this like purple and blue overlay shows what this looks like in a molecular gas tracer. So this is the carbon monoxide line, which is tracing kind of dense molecular hydrogen in our galaxy. And you can see that if you had eyes in the millimeter, you would be able to see all that dense gas that's forming new stars in the Orion Nebula that's not as prominent elsewhere in our galaxy. So this carbon monoxide line is one of the key ways that we can study gas in other galaxies because it's so bright. So here's an example of the nearby galaxy pair. This is M51 and its companion M51b that are currently merging together. So here's what this galaxy set looks like in visible light with stars. And if you look in tracers of the molecular gas or the atomic gas or the ionized gas, you can see that these trace the spiral arms in different ways, where the molecular gas is stronger near the center and the atomic gas stronger near the outskirts. This gas traces the fuel for star formation in these galaxies. And so by looking at where this molecular gas is, you can see where in other galaxies the young stars are forming. Even though these regions, you can see, you can hear where it's actually kind of a dark spot, these regions are usually obscured by dust that goes along with the gas. So they can be difficult to study directly in the optical. So we can look at the different ways that this gas is affected and disrupted by ways that galaxies can mess it up. So here's one of my favorite examples. This is the galaxy M82. Some of my favorite images in astronomy. This is a composite image where in blue you see what this looks like in the optical. If you look at this through the telescope, it's actually not, it's called the cigar galaxy, because really just you see this. But if you overlay what the ionized gas looks like, you see the incredible plumes coming out of the galaxy. And this is because this galaxy is forming stars at such a high rate that the young, newly formed stars are driving winds that are pushing the gas out of the galaxy. So something like this you can use to study how galaxies evolve by saying, well, if this galaxy is literally pushing the gas out because of its intense star formation, maybe that's how galaxies change. We call this feedback because as it's a feedback process where you form stars, and those stars drive winds that push out the gas. It's negative feedback where you can't have runaway star formation because you form more stars, you disrupt other gas. So it's like a self-regulating feedback process where that gas is pushed out. Right, so this is one example where we think stars can do this, young stars. Another way that gas can be disrupted is from accretion onto a black hole. So this is probably gas accretion instead of accretion by stars and tidal disruption events, but we're working on answering that question of if TDEs have something to do with it too. So here's the galaxy stars A. This is what it looks like in visible light. It's kind of just a big round galaxy, but you see this kind of lane of dust at the center. And if you look at it in other tracers, you see a different story, where in the radio it has these big plumes coming out of it, as well as in the X-ray from these energetic jets that are being driven out from accretion onto its supermassive black hole at the center. And so this feedback from, we call this AGN for active galactic nucleus. That feedback, again, either from the stars or from the black hole, can also really affect the gas. So this is the combination of millimeter light in teal and in pink there, as well as the visible light as a background, showing where fuel for star formation could be in this galaxy. And you can see it's kind of being ripped up a little bit by that jet. This is one of the most dramatic examples that we have in the universe, but it typically doesn't work out this way. And you might ask, well, if this, we see the examples of feedback, does that work all the time? And we don't see this often enough for it to be the whole story. So people work on simulating, well, how much energy would you need and how often to understand how this works. So I want to show a video of how one way that can work. So this is a simulation of two galaxies. So it's a hydrodynamical simulation. So it has gas and also stars and gravity. This was done at NCSA by folks at NASA, as well as some people who are currently at Harvard and Santa Cruz. And so during the merger of these two galaxies, you see that, you fling out a bunch of stars and a bunch of gas, and eventually they will come together. And one of the things that happens during this process is that the gas, that fuel for star formation in these galaxies, also gets flung and compressed, and actually can drive new stars to be formed in a large burst. So at this point, you see this intense white light from new stars being formed in the simulation. So you have a combo of new stars forming and gas being flung out, stars being flung out. And you can see that you're changing the shape of the galaxy as well, where you've lost all the spiral arms and now you kind of have a blob in the center. Some of these things are coming back. The simulation is pretty, and so one of the key things is figuring out how do you match this to observations. So I don't know if you can still hear me. My Zoom is giving me an error.
Oh, sorry. Yes, I can. Oh, we can still hear.
Oh, okay, cool. It might still something quit. But... Anyway, yeah. So then I don't know if I cut it out at all, but we can match these simulations to what we see in optical light pretty well, since we understand these features and how gravity makes them work. But there's still a lot of disagreement between what simulations predict should happen with the gas and with these jets driven by black hole feedback or stellar feedback, and what we see in real galaxies. And so this is what I'm working on now, using observations of that molecular gas. So these tracers are in the radio and submillimeter. So I use facilities like ALMA down in Chile, as well as for people who use the VLA, as well as optical facilities to look at what happens to those black holes. And we look at this black hole feedback using observations in the radio and the optical as well. And even some of these supernova surveys, we can use the data to figure out how often this kind of thing might happen in galaxies. So yeah, with that, I will take any more questions. And if anyone's watching this recorded, you can definitely reach out to me via email and ask more questions if you'd like.
Yeah, okay, thank you, Professor. Here are, during the RSVP page, we have some questions that students ask, although they can't make it today, but would you mind if I ask here for them? And then,
yeah, of course.
So first, what do you have? What's the advice do you have for undergrad trying to figure out what field of research to pursue? I think this probably asked by a freshman.
Yeah. So the first thing I would say is really try to seek out research opportunities. So there's a number of RUs that are put on through the NSF, as well as a number of smaller programs that individual universities will put on. So for example, if you're interested in astronomy, different observatories will often host summer programs that can be really valuable for getting that hands-on and research and figuring out if that's something that you like. There's also certainly smaller programs or things that are less intense than like a whole summer that are good for kind of building up your resume for those summer programs. Let's see. And then for figuring out your interest in terms of research, going to presentations in physics and astronomy of people, even from outside, talking about their research can be really valuable. One of the things that's great about the Zoom talks actually is the first 10 minutes of a colloquium or seminar is often really general. And whereas in a real talk, especially if it's in a small room, you might not want to go to a talk and have 15 minutes of interesting and 45 minutes of real technical. In a Zoom call, you can basically walk away without bothering anyone. Really, go to the first 15 minutes of the colloquium. Once it gets technical and it's just not interesting anymore, just sign off. It doesn't bother anyone. And I think people, at least I would be flattered if someone said, hey, the first 30 minutes was great. The rest was over my head. Didn't like it, but I didn't watch it. Like, that's more than fine. And especially when you're not in a physical room, you're not going to bother anyone if you walk away. You're muted, right? So don't feel bad about going to just the beginnings of talks. Take advantage of Zoom to do that. You also might find opportunities that are also on Zoom at different institutes that are easier to go to now that it's all virtual. So for example, different universities, or like the Aspen Center for Physics has a colloquium series that's all virtual. And if you want, if you're interested in a certain area or a certain place, you might reach out to one of your professors here or someone there and say, hey, I'm interested in listening to some of your talks. Do you have a mailing list that I can be put on to find some of those? People are happy to share those resources and have more people listen in. Let's see. Yeah, but yeah, I think that there's obviously like a lot of downsides to our global pandemic, but the ability to quickly duck in and out of interesting talks is potentially an upside and something that's easier to go to than having to haul across campus to go to a talk. So I definitely encourage you to do that.
Yeah, thank you, Professor. Yeah, I think reaching out is never hurts to do. Yeah. And Brian, do I have a question?
Yeah. Hi, Professor Decker. I'm Brian Wing. I'm the secretary of SWIP. our organization is really focused on women in STEM and other minorities within STEM. Do you have any advice for people that are like women or other minorities in STEM to get into research, and any problems that you face that you would have advice on?
So I think for me, like the thing that has helped the most is talking with people who have had who have a similar background and seeing what they've gone through. I feel like I must say that's rather meta, since that's exactly what you're doing, and having these talks. But for me, it was useful to have opportunities to ask questions about kind of the details of people's lives and how that worked. So for me, when I was an undergrad, I was really concerned with, can I have a family while doing this as a career? And so I talked to, I went to, events for women in STEM, and really tried to seek out like a library of life paths that people have had as kind of ways of thinking about my career path and how that might work. Just because people, you look at any individual's life and, that's not going to be what your life is, but somewhere in, the vast, set of trajectories that you can learn about, you can see how your life might fit in if you see enough of those, if that makes sense. And so kind of continually seeking those out for me has been really helpful. One of the ways that you can do that now that we're all at home is, at least in astronomy, there's a blog that's run by I forget the acronym, the Committee for the Status of Women in Astronomy. As part of the American Astronomical Society, they have a blog that's about women in astronomy, and so people talk about kind of their personal experiences. So having a partner that you meet when you're an undergrad and trying to move with them throughout your career, and how that works, or if you have a kid as an undergrad or as a grad student or as a postdoc or as a faculty member, how that plays into your life. Those experiences I think can be really helpful to read, even if that's like a far off thing, for your life. It's something that I was worried about, and I was really like reassured, kind of reading through the variety of ways people have managed to make research fit into their lives, since that's the right way to do it. You don't want to make your life fit into research, make the research fit into your life. Yeah, so I think for me that's been the most helpful, seeking out those stories, and getting that advice, which I realize is meta because that's what you're doing, but yeah, you're on the right track if you're if you're involved in SWIP. So
Yeah, thank you, Professor. I think, yeah, both research and life are important for us. And another question is, what's the most what's the most difficult challenge that you have overcome in your career, and how does that affect you?
let's see. I don't know how to answer that. Let's see. I think the most difficult challenge for me was really trying to hone in on how do you pick out good ideas, and how do you when I started grad school, I was really worried, like, I have to make a thesis of something that's new. Like, how do I find ideas that are new and ideas that are interesting, and ways of sussing out new things about the universe, right? Like, what does that even mean? Fortunately, that's what grad school is teaching you how to do that. But that is, like, obviously in retrospect, but at the time, I don't know if future me would have been able to convince past me of that. So I think like that process where my grad advisor was really key in helping me try to develop this, is not one event, but just like a series of events of saying, this telescope proposal deadline is coming up, are we going to use this telescope to ask an interesting question, and going through that exercise. So probably the answer to that question is the entire process of grad school and getting a PhD, which I realize is a weird answer, but kind of the whole evolution of that and the work that went into that is a series of things that are small, like by themselves, but as a whole experience, you know, an incredible amount of change.
That makes sense. Okay, thank you, Professor. And we have another question. What made you choose astronomy as opposed to other fields in physics?
Yeah, so when I was an undergrad, I did summer research in a few different areas. I started off, I knew I wanted to do like astrophysics, and I got to college and I, saw what people were doing, and I thought, there's so many more things. I actually want to do material science. And so I went and I did kind of an internship thing during the semester, and I realized that I hated engineering. So I did not go into that. I went back to physics and astro. And someone I knew was working at the observatory, and I thought that would be fun. And so I tried to get an introduction, and I wound up working at the observatory, the campus observatory over the summer. And that was a lot of fun. I liked working at the telescope. It was a smaller observatory, old school, where we were outside setting up the telescopes, and I had a lot of fun doing that, developing some of the procedures for using the instruments. And that made me more interested in optical astronomy. And so after that, I tried to find another summer internship project. And along the way, got distracted by, I mentioned that I kind of double majored because I took a bunch of weather and meteorology classes. And so I was interested in maybe going into atmospheric science. And so I talked to someone who was in atmospheric science and said, well, since you have this experience with astronomy, why don't you work at something that's both atmospheric science and astronomy? So I wound up working with some atmospheric scientists using they had models of different circulation models for different kind of simulated planets. And so I spent the summer trying to predict what that would look like as an exoplanet. So kind of using both worlds, which nowadays is like solidly in astronomy, but at the time was kind of at the boundary. But now that's regularly done in astronomy, and so that was a lot of fun. But I wasn't really sure still that I wanted to do astronomy. And there was an internship, like a summer internship away from college that was at Fermilab back in Chicago that I applied for. That was in accelerator physics. And so I thought, well, I always kind of liked particle physics. Maybe I'll try this internship. So I applied for that. I got into that. And my project was like not in particle physics at all. It was in more accelerator physics. So the physics of how do you accelerate particles to collide them, and all of the cool kind of engineering that goes into that. So that was a lot of fun. And I decided, well, I like this. I like astronomy. I have to apply to grad schools right now. I'm going to apply really, really broadly. I don't know if I'd recommend doing this, but at the time I was, just really undecided about where I wanted to, what I wanted to focus on, since everything was, I was generally interested in this variety of things. So I applied to programs that had strong accelerator physics. I applied to programs that had strong astroparticle physics, since that also sounded really cool. I applied to programs that had good astronomy programs. So all in all, I applied to like 11 schools. See, I got into 4, and they were across the board of interests. But I went to then go visit 3 of the 4. And in talking to different people at the universities, the one university that was really strong in accelerator physics, I went and I talked to the lab that I was interested in working with, and they did not seem like great people to work with. There was a lot of red flags. They told me that I had knew a woman who had been there, and she had since left. So I asked, why did she leave? And the person I was talking to, the leader of the lab, said something along the lines of, oh, well, women never really seem to stick around in our program. So to me, that was a huge red flag. They said a lot of things that seemed like the environment wasn't great. They told me that they assigned desk space to projects and not people. So if your project fell through, you stopped having a desk in the lab, and you weren't welcome anymore. I talked to someone else at the university who was, incredibly arrogant and seemed like he, was really, downright bullying to his lab. And I decided, this university isn't good. This department isn't good. I will not be happy here. And so I went on, my other visits and met some people who were happier. But the people who seemed like they actually were enjoying being grad students were all at Arizona, which is where I went. And so I thought, this is good. People actually seem like they're enjoying this as a process. I don't want to be miserable and bullied for 6 years of my life. So I talked to the person at Arizona who was working at kind of the area that I thought I was most interested in. And he had just started as a faculty there. So I met with him and I talked about some of the work that I'd done with like the atmosphere models. And he talked about some of the work that he was doing. And, in these grad school visits, you talk to a lot of people, and it's just a lot of talking with people who are kind of intimidating because they're professors, and you're trying to talk about what you've done but not seem weird. And so I'm trying to make some small talk at the end of the meeting. And so I ask, oh, since you just moved here, how do you like living in Tucson? And he told me, you shouldn't ask that to professors. It doesn't matter the city that you live. So don't ask people that. I thought, I have to live here for 6 years. I want to like the city. To me, it's important to, if you're moving your life somewhere, you should like
do you
it.
guys listening to the professor, or I think she's frozen?
Oh, I can hear her.
Wait.
I can hear the professor, and I can see her video too. It just looks like everyone else's video is frozen for some reason.
Yeah, I can't see anyone else moving, but I can't hear you all. That's weird.
I'll turn on my video if you want to see whether I can move.
Oh yeah, I can see you.
Yeah. Okay.
Oh,
Okay.
I think.
Yeah, everyone's moving now.
You.
Everyone's moving now.
Cool. All right. Yeah, that was too long of a story. Sorry, but basically, I talked with individual people who were doing stuff that I was interested in working on. Some people seem like we just would have a different view on work-life balance, especially, and the nature of research collaboration. I wanted to work with an advisor that I could collaborate with, and who wouldn't just tell me what to do and to keep my head down. And so I decided to not work on the exoplanets project anymore because of that interaction. But I did talk with more professors there who seemed genuinely interested in their research and wanted to collaborate and seemed to enjoy working with students and enjoy what they did. So I decided to go there. And over the summer, I had more interactions with potential mentors. And wound up working with the person who became my grad advisor, and we had a great kind of collaborative advising relationship, which was great. But really, being interested in so many things, I do feel like it served me well in being able to kind of jump into different fields like the tidal disruption events, but also for me, astronomy is really interesting, but without, astronomy is also about people, and without liking the people that you work with, collaborating is really hard. So for me, finding, people who were great to work with has been a big part of finding research projects that were also great to work on. Since the day-to-day of what you do, if you're calibrating a spectrum, is going to be much more about the people than the science. So yeah, it's I would say as you go into research, definitely Don't let people, push you around and, bully you. Don't put up with bullying just because the science is interesting, because there's a lot of interesting science out there.
Thank you, Professor. This is a really good answer to our questions. Does anybody have more questions to ask Professor? Hi, Manthan.
Yeah, I was just thinking of like how to say my question. When you were actually wait, I still need some time like properly like word the or like not word but like how to say the question.
Okay, maybe I can ask another question. So there are some other people ask what about the cultures in the university that you have either studied or worked at. Yeah,
The cultures?
Yes, the cultures, like the physics department.
Yeah, so every department will have a set of people that have developed this set of unspoken rules of how people interact and how science gets done. So for me, one of the things that I really value is being able to discuss new results in science in a way that's interactive and but also rigorous. And so one of the things that I really like about the astronomy departments that I've been at has been a tradition that we often call Astro PhD or Astro PH Coffee. As people submit new papers or have new papers accepted, they often post a preprint to the archive, which is free for anyone to read and use. And so that daily digest of new archive papers is kind of the main aggregator, at least in astronomy, I think in physics as well, for kind of the latest in the field. And so at the departments I've been at, it's really fun to have this either weekly or several times a week discussion where everyone gets together, has their coffee. Now we do it over Zoom and talks about interesting new papers that have come across in the archive. And as a grad student, this was really useful to me because it was even just being a kind of a fly in the wall of that discussion of what's the context behind these results? Like why is this paper coming out now? Oh, it's because this person has been working on this instrument and this instrument is new to this telescope and now it's commissioned and this is new data from it. And as I go on my career, it's really useful to have those discussions and say like, look, this paper is out. I'm really excited about this result. It's a really cool improvement in this field, and we've been working. The field has been working towards this for years, if not decades, and having those discussions about not even just the individual paper, but kind of the state of different fields as they evolve. And so those places for discussions, I think, are one of the ways that in astronomy we kind of have this good and productive culture.
Yeah, thank you, Professor. Hi, Manthan. Are you decided? Yes, go ahead.
So, as someone that like had many interests and was like considering many different fields, what advice would you give to like undergrads that like have interest but like are unsure about like whether there's something else they might enjoy more or like are still searching for in terms of like both research and classes?
Yeah, so I think finding like small ways to try out different things is really helpful. So for me as an undergrad, a big part of that was lab classes. There was one required lab for each major that I was in, but all in all, I wound up taking, I think 5 lab classes, just because I thought that I really enjoy them, which, now as someone who works in observation, which is like the astronomy version of experiment, is close to what I do. But I found that the labs were a good way of getting introduced to not just the materials that, the different research topics that you might work on, but also the techniques that you use for the different different areas of research. So taking all of the physics labs that you can, I would definitely recommend that you take that advanced physics lab that's offered, where you kind of reproduce, historical experiments and make the measurements, and get practice like analyzing the data. But for me, I also took the atmospheric sciences lab. I took the astronomy lab. So if you're interested in astronomy, taking the astronomical techniques class, I think would be a really useful way to get some exposure to, not just the active research topics that definitely will be covered, but also things like, well, do I like looking at spectra of galaxies and trying to interpret those? Which seems weird, but it, certain kind of areas of scientific practice might click more or less to you. And knowing more about the mechanics of exactly how that research is done, I think can be really useful in knowing how interested you are in it. For example, if, dealing with data and dealing with the calibrations of optical data in a class just drives you up a wall and you just can't stand the, uncertainty of that, or, when the data are bad and have these, defects in them, if that just drives you up a wall and it makes you unhappy, then computer simulations of galaxies, maybe that's really neat and tidy and you don't mind that, you might not know all of the physics that went in it. It might not be complete yet. Maybe you like the more elegant simulation side of things. That kind of like personal connection to the techniques, I think, can be really valuable for choosing a field. Since, definitely ask other people this question, but for me, I think it's all interesting. And so, picking the topic is more picking the kinds of techniques that I think are fun to use on an interesting problem. And especially now in science, where there's techniques such as like working with big data that you could use on a lot of problems. Figuring out what will let you use, say, a cool tool like that can be one way of finding interesting research topics in a way that also gives you kind of an edge in working on it.
Yeah, that was helpful. On the topic of observation versus theory, how interchangeable are those two fields? Can you work in both, or are they like very separate fields which you have to like branch from eventually?
So in astronomy, I don't know that much about physics. Will be different, like particle physics or like condensed matter will be different. But in astronomy, many people do work in both. So especially, but there's also a limited number of things that you can specialize in. So for example, if you, some people will work in observations where they know the ins and outs of everything can go right or wrong, going from photon to mirror to second mirror to, to camera to, all of the mirrors and optics that are bounced off to the CCD, to every aspect of the analysis, every aspect of the calibration, and every aspect of how you calibrated it to a final data product. If you know the ins and outs of that in a bunch of optical telescopes, that's a lot of time you spent developing that expertise, a lot of things that you can use that on, that you probably also don't know the ins and outs of exactly how you code up the biggest n-body simulation that's being done at NCSA. But there are people who work in the bounds of both. So let's say you collaborate with people who know the ins and outs of all of that, the optical telescope, and you get the spectra. And, you can ask them like, I did this, it's probably good enough. And now I want to compare it to the simulation. There's definitely people who you can kind of think about it as some people are really just like the master of like one specific trade and know it inside and out. And some people work at a little bit less depth in multiple different fields. So I'd say it's common for people to really pick one. But depending on the depth that you explore different things, people will work in both. This is especially common in fields that are newer. So in fields that are newer, where there's less kind of entrenched expertise, you kind of have to work in all the different areas if you want to compare simulations to data, say. So most people pick one. So for example, I don't work in theory. I don't make simulations, and I don't do analytical work. But I did work a little bit on theory as a grad student. I worked on like the outputs of simulations and used that to compare to data. So that paper had no new observations in it. So it's like technically a theory paper, but I wouldn't really have called myself a theorist. And that kind of in between space, there's a lot of work that that is done, especially as we get more data and more simulations that make data. And so it's not like by picking one thing, you're like stuck there forever.
Thank you.
Thank you, Professor. Okay, as our ending traditional question of a SWIP. So if you have a superpower, what do you think it would be?
Let's see, definitely teleportation. I spent way too much time on planes going to telescopes during my postdoc, so that would have been nice. But also, like so much of astronomy is the limitation of having a 2D view of everything, and if you just teleport and then teleport back before you even needed to like breathe, like what could we do if we could see the other side of the Milky Way? We'd be, like 100 years advanced in what we know about physics. So yeah, definitely teleportation. So if you go into a different part of physics, please work on that.
That's a great question. That's a great answer. Thank you, Professor. Okay. Thank you all for coming for this midterm busy week, and we're happy to have Professor French to come for talk today, and that's all. And if after that, if you are interested in more events of SWIP, you can subscribe our email and get our updates. Thank you, everyone, and thank you, Professor.
Yeah, thanks for having me.
Thank you.
Bye, everyone.